At Tailor's shop, a client stands on the fitting platform. The tailor has 3 approaches to fitting the suit: minimize the gaps, model the body shape, or generate an entire wardrobe of possibilities. Same body, 3 fundamentally different philosophies: least squares, maximum likelihood, and full Bayesian estimation. Least squares: the tailor measures the distance between the fabric and the client's body at 20 points: shoulders, chest, waist, hips, arms, legs. She adjusts the suit to minimize the total square distance across all 20 points. The squared distance is the residual. Minimizing the sum of squared residuals is ordinary least squares. It's simple, fast, and has been the default fitting method for 2 centuries. For a client with a standard body shape proportional, symmetric, the suit fits well. Now a client with an asymmetric build, 1 broad shoulder, 1 narrow. The left shoulder is 2 inches wider than the right. Least squares minimizes the total gap, so it compromises. The left shoulder gets a suit that's 1 inch too tight, and the right gets one that's 1 inch too loose. Neither side fits well. The symmetric optimization can't handle the asymmetric body. This is exactly what happens when data has non-Gaussian errors. Least squares assumes symmetric, bell-shaped residuals and produces a compromise that fits nothing well. Maximum likelihood. Before adjusting the fabric, the tailor first asks what kind of body shape this client has. Athletic, broad shoulders, narrow waist. Pear-shaped, narrow shoulders, wide hips. Asymmetric, one side broader than the other. She selects the appropriate body shape model, the likelihood function, and then finds the suit parameters that are most likely given that model. For the asymmetric client, she uses a skewed distribution. The suit is designed to accommodate the asymmetry from the start, not compromise around it. For a perfectly average client Gaussian body shape, the least squares suit and the maximum likelihood suit are identical. This isn't coincidence, it's a mathematical theorem. When the residuals are normally distributed, maximizing the Gaussian likelihood is algebraically equivalent to minimizing the sum of squared residuals. The 2 formulas produce the same answer. This is why least squares has been so successful. For most well-behaved data with Gaussian errors, it is maximum likelihood. For the asymmetric client non-Gaussian body, the suits diverge. Mull with a skewed distribution allocates extra fabric to the broad shoulder and less to the narrow one. The fit acknowledges the asymmetry. Least squares forces equal treatment of both shoulders and achieves a mediocre compromise. In pharmacokinetics, drug concentration data often has non-Gaussian errors, log normal or heterostatic. Mull with the correct error model produces more accurate PC parameter estimates than ordinary least squares, especially for drugs with high variability. Least squares minimize the gaps, implicitly assume Gaussian errors. Asked, simple, 2 centuries of theory. Maximum likelihood, model the body shape explicitly, then find the best fitting parameters. More flexible, handles non-Gaussian data. For Gaussian bodies, they produce the same suit. For everyone else, will produces a better fit because it respects the actual shape of the data.